During the last 2 decades, Jon Kalb, our keynote speaker, has written C++ for big shots like Amazon, Apple, Dow Chemical, Intuit, Lotus, Microsoft, Netscape, Sun, Yahoo. That's a long list. Very impressive. Jon chairs the board of directors for the Boost Foundation and serves on the board of the C++ Alliance. He enjoys public speaking and training in C++. He's active with the Silicon Valley C++ community and speaks at and chairs at the C++ track for Silicon Valley Code Camp. So we present to you Jon Kalb with his keynote. I wish we had the in-person applause. Hi, Jon. What's up?
Hello. Thank you very much for that welcome. All right, I'm going to share my screen here. And it's great to be here. Happy India Day to everyone. And it's special, it makes it particularly special to be here for this event. Can you see my screen?
Yes, Jon.
All right. Should we go ahead?
Yes, please.
All right. Excellent. So the title of today's talk is C++ Today, the Beast is Back. My name is Jon Kalb, and this is the same title as the book that I wrote with Gasper Asman. And in a sense, what we're going to talk about today is kind of the story of this book. This book is a book that you can get free. You have to send them your email address, but if you go to this URL and give them your email address, you can get a copy of the book free. Now, why would Tim O'Reilly of O'Reilly Media, why would he pay Gasper and I to write this book if he was planning to give it away? And they did pay us. They didn't pay us very much, but they paid us to write a book that they literally give away. And why would they do that? Are they crazy? No, no, no. This is actually a business technique that they do. When a new technology, a hot new technology comes out, they want to do what they call a report. So as you see, the book is not very long. It's about 60 pages. It's an enjoyable read. It doesn't go into a great deal of technical depth, but it gives you a little bit about perspective about C++, which is what we're going to talk about today. But what is their business model here? Well, the business model is they want to write other books, more in depth, bigger books that they're going to talk about C++. And so they want to get email addresses. They want to be able to have things that they can pass out at conferences and things like that. But remember, I said new technologies. Is C++ a new technology? C++ was first being developed in the late 70s. In a sense, C++ is a very old technology. But O'Reilly understands that although it was an old technology, it's also becoming a new technology. And that is really what the story of this talk today is about. It's about the beast coming back and coming back in a big way. So we're going to go back in time. And I wish that we had some audience input. I would ask you what this is, but I'm sure a lot of you recognize that this is a model of the difference engine. And that fellow peeking out from behind is Charles Babbage, who designed and built the original difference engine. And the reason I talk about it today is because the software, if you will, the code for what the difference engine was going to do is actually encoded in all those gears. The hardware and the software are essentially combined in the design of the hardware itself. But this gentleman here, this is John van Neumann, and he noticed or made the observation that computers operate on data and programs are really just data. So really a computer should be able to store the program in the memory of the machine that is also used for data. And we call this the von Neumann architecture. And today modern computers all use von Neumann architecture. Now, again, I'd like to be able to ask you if you can recognize this. I'm certain most of you recognize that this is assembly language. And then I would ask you what, and it's actually for the 6502. It's the only assembly language I ever really learned in any depth. And of course, assembly language is kind of a misnomer because there isn't an assembly language. Every platform has its own assembly language, which is really just a collection of mnemonics for the specific arguments, or excuse me, the specific instructions that computers are able to obey. And the reason that we have assembly language, of course, is that if you're a computing professional, some of you may recognize Ada Lovelace or Alan Turing, but if you're a computing professional, the expectation in the early days, of course, was that you would write in assembly language. Now, why is that? Well, because computing professionals need two things. Computing professionals are writing system software. They need to have access to all the features of the machine. Also, they need great performance. If you're writing an application, it's not necessary that all of your application run fast. Parts of your application that aren't done very much and are not critical, those can be written in a less efficient way. But for system software, everything needs to be fast because applications depend on all system software. And so we really need performance. And so the assumption, of course, is that computer science people and people writing system software are going to write in assembly language. Now, contrast that with scientists. This, by the way, is Elizabeth Lee Hazen and Rachel Fuller Brown. They developed nystatin, which is the first non-toxic drug treatment for fungal infections. And they're scientists. Now, I don't know how much they actually used computers in their work, but a man named John Backus created Fortran. It's our first compiled language, specifically to make it easier for scientists to be able to write code to solve problems. And because, as you might guess from the name, Fortran, it's a formula translation language. And the idea is that it focuses a lot on using arrays for performance, but also does a lot of floating point mathematics, because of course, that's what scientists are interested in. Now, what if you're one of these guys? What if you're a business person? Well, you have different interests. You're maybe less interested in floating point, but you're much more interested in being able to do text processing and also to be able to do binary coded decimal, which is a way that we can encode numbers in the way humans think about them into the computer. And those things are often the technique that was used in particularly in business programming. And so very, very early on, computers and even languages were divided into those things that scientists would use and those things that business people would use. And this was designed to be a business computer. This is the Univac. It was released in 1951, and it was marketed as for business and government. In other words, this machine didn't do floating point. What it did was text processing and binary coded decimal. Then in 1962, DEC sold this machine, which is called a Link, and it was sold to laboratories. And this does floating point calculations. And of course, it does some text processing, but it's not optimized for text processing. And it certainly doesn't do binary coded decimal. And then when we get to the 1960s, IBM did something that cemented their lead as the top computer manufacturer. It was already the top computer manufacturer, but then they released this. This is the System 360. Now, you might see that little red button there, and you might guess what it's for, but there were a number of, with big mainframes being developed in the 1960s, there were a number of science fiction books with the theme that computers were taking over, and there was some great fear about computers. So IBM actually put a big red button right on the front. That's the power switch. If you slam that button, the computer will stop taking over the world, no matter what it's doing. So that's what it's for. Now, you might wonder about the name 360. Now, when I first heard the name 360, I didn't wonder. I just thought it was some marketing thing. I used to work at Boeing, and I can tell you what Boeing 707 and 737 and 747, I can tell you what those numbers stand for. Absolutely nothing. Marketing just thinks they sound cool, so that's what they give. But the 360 in the System 360 actually does mean something. It meant 360 degrees. And what this meant was, this is the solution to all problems. At least that's the way IBM was marketing it. It said, Now one new computer for all data processing needs. And by all data processing needs, what it meant was science and business. Well, how do you achieve science and business? Well, what they did was they took the instructions for floating point and that anyone would want, all the instructions from scientific computing, and also added all the instructions from business, the text processing instructions and binary coded decimal. And so what they actually designed then was a machine that featured binary decimal and hexadecimal floating point. We had floating point operations all over the place. The instruction set was so complicated. It was the first instruction set that was actually implemented in microcode rather than implementing it directly in the hardware. This was truly a machine designed to be able to do whatever kind of programming you wanted to do. And because they were processing text, they did something. They weren't the first company to do this, but they established this as the standard. And that is that every 8-bit byte had its own address. Now, we're so used to this now, we don't even think about this. But in early hardware, sometimes a byte would be 12 bits or 10 bits or some other thing. And there were all sorts of different ways because in trying to save on address lines in the hardware, if you didn't address small items like 8 bits, it didn't have its own unique address. Instead, we would do tricks like have instructions that says, well, operate on this part of the thing that has this address. So you could have a word that would have multiple bytes in it and process it that way. When IBM set the 360 up and said, this is how we're going to do it, it set the standard for the industry, which is how it's been followed since. It effectively established what we would call the C machine architecture a decade before C. So now we get to the 1970s and we can start talking about C. This is a photo of Bell Labs. And Bell Labs had 3 important things that led to the creation of Unix. The first was they had researchers like Ken Thompson and also Dennis Ritchie. They also had a need for a document processing system. So Bell Labs was creating a lot of patents, and patent submissions needed to look very professional. And so they were individually typeset, which was kind of an expensive and also time-consuming process. And the other thing they had was a little used PDP-7 in the corner. Not this particular one, but this is a picture of a PDP-7. And Ken Thompson wanted to be able to play with it. And so what he did is he essentially made a deal. He said, if you'll let me play with this, I will create a document processing system for you. In other words, a typesetting system. So they wouldn't have to have dedicated typesetting machines and dedicated typesetters. And so for those of you who have used Unix, you know nroff and troff tools for doing typesetting. Those are the reasons Unix was created, was specifically to support those applications. So now I'm going to ask you, what language was Unix written in? And a number of you know, well, you're going to say C, but it turns out, no. Remember what I said. System software people write in assembly language. Exactly. So Unix was written in assembly language. But wait a minute, I thought Unix was written in C. What happened is when we get to Unix version 4, we decide, or the Unix developers decided that they wanted to be able to port Unix to other platforms and not just run it on PDP. Well, what do we do about that? Well, we have 2 choices. One is we could rewrite Unix from the ground up for every platform out there, or we could rewrite it once into a language that is a portable assembler. And that is essentially what Dennis Ritchie created, was a portable assembler. And it turns out that this was an amazing success, because I remember I told you that we have Fortran to make lives easier for science programmers, because they don't need to know the details of the machine. They don't need to exploit every feature of the machine. They just want to be able to write correct programs that are portable on a number of platforms. And business people were in the same situation. They didn't need the full power of the machine. They didn't need all the features of the machine. They wanted to be able to write code that could be run on any machine, and that's why they had COBOL. But the thinking was, well, you know, systems people, they don't need that. they're going to always want to write in assembly language. Turns out, no. They want to write in portable assembler. They don't want to be bogged down in the details of the machine. They just want to write code that is both portable, but also low level in performance. And that was the sweet spot for C. And that made C an incredibly powerful and very popular language. So now we've moved on to the 1980s, but I'm actually going to now step back in time because I need to introduce these individuals here. This is Dahl and Nygaard, and some of you might recognize who they are. They won a Turing Award for ideas fundamental to the emergence of object-oriented programming through their design of the programming languages Simula 1 and Simula 67. These gentlemen essentially invented object-oriented programming and coined that term. Now, it just so happens that this man, Kirsten Nygaard, was a faculty member at a university in a small town in Denmark that happened to be the hometown of Bjarne Stroustrup. So he actually is the individual that taught Bjarne Stroustrup how to do object-oriented programming by using Simula, which he had created. Then when Bjarne went on to do his graduate work, he attended in Cambridge, Churchill College. And what he did was for his PhD dissertation, he needed to do research, and he did a simulation of a computer network in order to get the information that he wanted for his dissertation. Now I'm going to kind of break a rule of great presentations, and I'm actually going to just read to you some text on the screen, but I think it's very important. This is what Bjarne said about his experience. He said, so I rewrote my simulator from Simula into BCPL. I guess I skipped a step here. I should tell you that when he wrote the simulator initially and wrote it in Simula, because this is what he was taught to do, and ran it, it took down the computer. The administrators actually kicked off his program because it took down the entire computing system for the college. And so that's, if he wanted to get his work done, he needed to do something else. So that's why I say, so I rewrote my simulator from Simula into BCPL. BCPL was a predecessor of C. And all of the high-level structure disappeared. All of the nice organization that had helped me debug and helped me design disappeared. But the resulting BCPL, once I had debugged it and lost half my hair in the process, ran really fast. It could use all the resources of the machine. It could communicate with anything on the machine, and I got my data and I got my PhD. I came away with the opinion that I would never again want to attack a problem with tools fundamentally unsuitable. And in particular, I don't want to make the choice between elegant, which Simula was for this problem, and efficient, which BCPL was. I want both. And that has been sort of one of my guiding lights. If you give people the choice of writing good code or fast code, there's something wrong. Good code should be fast. And the reason I have read this is because this is so much the guiding principle of C++ that Bjarne started to appreciate even before he started working on C++. Bjarne accepted a position at Bell Lab and therefore learned C, which was, as I said, a derivative of BCPL. So he understood C very easily, but he started working on a next generation language that would support the higher level abstractions that he was used to with Simula. And so he started to work on what was originally called C with classes in the late 70s. And then in the early 80s, it got renamed C++. And during the 1980s, the number of users doubled about every 7 months. And so it really started to take off. Now, I'm going to take a bit of a break from history and answer a question, which is, why C++? Why is it that software engineers are attracted to C++? Well, one of the things that I'm going to focus on, and I'm not going to read all the things that I've got on my slides here because I really want to focus on a through line, which is high-level abstractions at low cost. And I want to dig down into that. There's a whole bunch of abstractions I've listed here. I'm not even going to list all of those, but conceptually, I want you to understand that the idea that separates C++ from its predecessor, which was C, is that C++ supports a number of high-level abstractions. Simula, of course, supported object-oriented programming. C++ also does that, but there's a number of other abstractions, but they are not, they are always delivered in such a way that they do not compromise performance in giving you those techniques. And one of the most important things that we can do in C++ is we create user-defined types. And the reason this is so important that this be an efficient thing is that that's how we solve problems in C++, is we create a new type. You have a job you need done, we create a type that does that job. That's how we do it. And so if creating new types had overhead, that would simply be an unacceptable burden for us. So I want to point out that we can create fundamental arithmetic types in the library. The complex numbers, which are fundamental arithmetic types, but we don't have them as base types in the library. Instead, they are, excuse me, in the language. Instead, they're in the library, because the library is powerful enough that we can write efficient operations. We don't need to move complex numbers into the language itself. We talk about things like object pointers and function pointers. We can write our own versions of those, which will be as efficient or even possibly more efficient. Function objects can be more efficient actually than function pointers in some contexts. So the ability to do this is an important feature of C++. Because it supports these different abstractions, it also then supports a number of different paradigms. And the nice thing about the way that C++ works is that it allows us to pick and choose the kind of paradigms we want to work with for any particular part of a problem. And we can even mix these paradigms so that we have a number of different combined approaches to solve problems or challenges. I think of C++ as a language specifically designed to make writing powerful, useful libraries. This is an awful lot of the feature set of what's in C++ are things that many programmers won't use on a day-to-day basis because they really are designed to make libraries more powerful. And so we tend to use those libraries on a day-to-day basis. And so we use these features only indirectly. I want to talk about one of the key abstractions that Bjarne refers to often, which is the zero overhead principle. And I want to explain what we mean by the zero overhead principle, because it's a little bit of a misnomer. Some people think it literally means that we won't have any overhead at all. That's not what it actually means. What it means is, first of all, if you don't use a feature, you don't pay for the feature. We don't add features to the language that are going to have any impact at all on existing applications, because obviously they aren't using that language. So we can't slow down the language by adding a new feature. But the other thing that it says is, if you do use a feature, you pay no more than you would if you coded it by hand. So that doesn't mean there's no overhead. It just means that the overhead that using a language approach cannot be greater than what the language, what the overhead you'd be if you coded it yourself. And that is our guideline for when we think about and what we think about we're going to do for C++, both actually in the language side and also in the library side. So the other important part of power is that C++ not only has these high-level abstractions, but because it is effectively a superset of C, which is a portable assembler, it means that you have low-level power when you need it. You can get right down and manipulate hardware at a device level that you simply can't do with many languages. So one of the things I want to point out, and this is just out of many things we could point out, is that in C++, as in object-oriented programming languages, there's a way to say, I want to create an object, putting something in memory, and I want to initialize it. I want to put it in a useful state. And of course, every object-oriented language, of course, has that kind of feature. But with C++, you not only can put this on the heap, you can also put it in static memory, or you can put it on the stack, or you can even put it in arbitrary memory. And that's the kind of thing that we would need, because as C++ programmers, we don't want to have an arbitrary restriction that simply says when you create an object, you have to create it on the heap. That would be unacceptable to people who are doing systems programming or the kind of programming that we want to be able to do in C++. There's a number of low-level techniques. I'm not going to get into all of these because we're trying to cover a lot of topic in only an hour. There's also a wide range of applicability, not just in terms of domains, but also in terms of sizes. You can be writing something that's as small as a device driver or as large as an application that's going to be implemented with a suite of machines. Because of the fact that the C machine, which is what IBM introduced with the 360, even before C existed, but that is the hardware model that hardware architectures make, and that makes it very easy to port C++ to all sorts of different platforms. That's one of the things I want to point out, and I will point this out because I think this is the one thing that makes C++ truly unique. C++ can be used as a systems language, but then so can C. But C++ also has high-level abstraction support that C doesn't have. But there are other languages that can be used as system languages and also support high-level programming. But the thing that makes C++ unique is that it has those two characteristics and also has a very, very large installed base. The number of books, the number of people like me you can hire to come train, the number of people you can hire to work on your program, the number of videos out there, the number of conferences out there dedicated to C++ is unsurpassed by any other language that has these features of being a systems programming language with high-level abstractions. And that's what makes C++ truly unique and special. I'm not going to go into alternatives to garbage collection, but as we know, in C++, we tend not to use garbage collection. We instead tend to use RAII techniques to do resource management, and we get better performance under better control by using that technique. So I want to thank Michael Case. I also want to talk about getting into the 1990s. So I mentioned that during the 80s, the audience for C++, the user base for C++ was doubling every 7 minutes, or 7 months. Sorry, not every 7 minutes, every 7 months. But when we hit the 1990s, something very, very special was happening in all computing, and that was GUIs. And GUIs were very often programmed and driven by object-oriented programming. Object-oriented frameworks were all the rage because this was the battleground for not just the Mac and Windows, but also OS X. There was a number of different object-oriented GUI approaches, and suddenly object-oriented programming was very hot. And the programming language that people looked at that associated with object-oriented programming was C++. It was during this period of time when a number of companies that had invested a lot of money in C++ approached Bjarne and said, we want to standardize C++. We want to make this an international standard. Bjarne agreed and started working with the committee on that. Now, one of the things that the committee did was they incorporated the work of someone who didn't do object-oriented programming. This is Alex Stepanov, and he was working on what he coined the term of generic programming. He had a completely different point of view. It doesn't use object-oriented programming. Alex was not a fan of object-oriented programming. There's no virtual functions in his library. What happened was the man here that you're seeing on the right was Andrew Koenig, and he had worked at Bell Labs with Alex Stepanov, and he contacted Alex and said, are you going to propose your library for the standards committee? And Alex said, oh, no. This library is not what the standards committee is looking for. It's way bigger than they expect. It doesn't use object-oriented programming, which is what everybody thinks of as C++. So no, it would be a waste of time to submit that. I'm not going to submit it. And Andrew's response was, well, I think you're right. I think the committee will not accept your library if you don't submit it. And so Alex and his team went without sleep as they put together a formal proposal for the standards committee, and it was in fact accepted, and we now call it the C++ standard library. And this is an amazing addition to C++. This supports a whole new way of doing programming, this generic approach to programming that Alex created and was implemented in in his library, which became the C++ standard library, is something that other languages just don't approach, having the ability to do this sort of thing. So the standard was released in 1998, and when that happened, this man, who's Beeman Dawes, he was the chair of the library committee, and he worked with other people in the standards committee to form something called Boost. And the goal of the standards committee is to standardize existing practice. But Beeman and Dave recognized that the problem with that is that the only libraries that were in widespread use in C++ at the time were proprietary libraries. There were libraries that couldn't be standardized. So how do we create a way of sharing libraries? Now, today we'd say, well, just put it on GitHub, right? Well, these guys were years ahead of themselves, because what they did was they said, we want to make a way of sharing peer-reviewed, high-quality, open source libraries where you just come to this website and you download the library. And at the time, that was unheard of. And it made, it did create a whole set of libraries, really, we call it the Boost libraries, but it's a whole set of libraries that were of very high quality and allowed C++, allowed people to experiment with new techniques for C++ and add lots and lots of usability and approaches. So what do we have? We have a language that was growing very quickly in the 80s. It became the go-to language for object-oriented programming in the 90s, when object-oriented programming was so important because of GUI. It became an international standard. It acquired the standard template library, which allowed for generic programming, a programming paradigm that was unheard of before then. And it established Boost as a place for open source software that was way, way ahead of its time. As we went into the year 2000, C++ was poised to take over the world. But that's not actually what happened. What happened instead is that Java became very popular. Why? Well, Java supports object-oriented programming. It became the language of the web, whatever the heck that means. Oh, it means the language of the future. So Java is the language of the future. And, you know, it's almost as fast as C++, and it's easier to learn and teach. You can almost imagine some professor calling the dean and saying, hey, you know, in the language, or in the class where we're teaching programmers, and, you know, everybody gets stuck on chapter 9 where we talk about pointers. You know, if we switch to Java, we would pretend that pointers didn't exist and we wouldn't have to teach pointers at all. What a great thing. So let's just talk about one thing I want to focus on, and that is speed. Because this was an interesting time in our history when desktop computers in the 2000s were so powerful that it seemed like operating systems had to use gratuitous animation to justify you buying a more and more powerful computer. The computers were just so fast that, I mean, they could calculate spreadsheets, they could do databases. You know, how much faster do you need the cursor to blink in your word processor? They were as fast as they needed to be. We finally solved the performance problem by just having really, really powerful computers. And if that's the case, then you start to think about, then do we need a computing language that is able to get the maximum performance out of hardware? Not if it comes with complexity, not if it comes with baggage. C++ has roots in C and carries C syntax limitations. It has a lot of complexity. Even though generic programming is amazing, it was complicated for some people. Operator overloads are intimidating. And did I mention that pointers are hard? Yeah, pointers are hard. So if we could go to a managed language, then we could avoid all these and our code would be almost as fast. And so there were a couple of families of languages, the Java family and the Microsoft CLI family, and they were embraced by colleges because there were companies behind these languages that would push them. Whereas C++, although it was created at AT&T, at Bell Labs, AT&T only saw C++ as a language for internal use and never really tried to push it on other companies, never tried to establish it as a standard. That happened entirely organically. When the Standards Committee shipped the standard in 1998, an interesting thing happened. This was not controversial at the time. In fact, it was actually true, but it was well accepted by people in 1998 that there would not be an implementation, a standard compliant implementation for 4 or 5 years. People recognized it would take that long for compilers and libraries to be able to deliver on the standard. And that meant that the Standards Committee decided that they were going to not push new features. They were going to take a break from pushing new features and essentially work on what you might say bug fixing releases of the standard, cleaning up the standard, making it more intelligible, making it more consistent, and working on the standard itself. That was, I think, the correct decision to make, but notice the effect that it had on the organization itself. What happened was a lot of people stopped coming to ISO meetings. They felt like it wasn't interesting if they weren't adding new features. And so we had this really terrible decade for C++ because there was no new standard features in the 2000s. There were a minor update in 2003 that added no features. There was a technical report, which is not technically part of the standard, but no new features for the entire decade of the 2000s. This was a time when Java was taking off. It looked like perhaps C++ was destined to be the new COBOL, a language that was only for legacy projects. It looked really bad, but that's not what happened. What happened is the beast came roaring back. Why is that? Well, one of the things to understand is that as desktop programs became very, very powerful, they stopped being what we thought of as computers. So what's a computer? Well, this is a computer today. We care about performance. Maybe we're less compared about how fast the phone is, but on how good the battery life is. And so we need really, really performance squeezing software in order to get the most out of our computers. And we also have these computers. So what is this? Well, this is cloud computing. And again, it's the same situation. It's a little bit different. I don't think these computers run on battery. Instead, we're concerned about getting performance per dollar of hardware or per dollar of power, or maybe even per watt of cooling. So there's a fellow named James Hamilton who worked at Amazon, and he did this cost profile for what he called the modern high-scale data centers. And just to explain what I mean by that, what he meant was these aren't just large data centers handling generic issues. These are data centers where they're essentially running the same software on thousands and thousands of processors. So in other words, it's running a search engine, or it's running something like Facebook or some application. And the reason that's important is because it's essentially the same software being run on hundreds, thousands of machines. And what he looked at for power, for cost there, I'm listing these in the order. The most expensive thing was the hardware. The next most expensive thing was power distribution and cooling, which ironically is actually more expensive than the power itself. Was getting the power to the machines and cooling the machines was more expensive than just the power. And then of course there's the network equipment and other infrastructure. The top three are directly related to software performance. If you can make your software 10% faster, you're going to save 9% of your costs on the bottom line. That's how important it is to get your performance right. Now, where are programmers and IT professionals? Did he just leave them out? No. They're in. That's what's other infrastructure. It turns out that hiring programmers is because we run the code they write on so many machines, the programmers' cost when spread out over these machines is not that great. And so what that means is that if you optimize for making it easy to write code, you're optimizing for the wrong thing. You should be optimizing for performance. And that's why C++ is interesting again. That and something that happened in 2011, which of course is that the Standards Committee finally, after 13 years, released an update to the standard. Bjarne said, it feels like a new language. If you look just strictly at the page count, that page count, of course, is not a complete, unambiguous indicator of the language itself, but it gives us a rough idea, and it looks like almost twice as many pages. That is how much was added to C++11. A lot of things were added to simplify the language. Now, if you think about it, I think most people agree that C++ is too complicated. That's the number one complaint about C++, and I think we all agree. The problem is the easiest way to solve complexity is to take out features. But if you take out features, you break code, and that's unacceptable. We're not going to break code. And so how do you simplify things? By adding. Well, it turns out this is one of the things the standards committee does. It thinks about what kind of features can we add to the language. That automatically makes the language more complicated, but it may make it easier to use. If we can add features that make it easier to use, the fact that old features exist, but if they're not used, it makes it easier to learn, it makes it easier to read the code, it makes it easier to write code. A number of things were added to make C++ more modern, Lambda expressions, support for Unicode, tuples, smart pointer, the kinds of things that we expect in modern languages. And as I mentioned before, C++ is all about libraries. So there are a number of things that were added to support library users. And then also some completely new areas such as move semantics. And although multi-threading has almost always been part of C++, multi-threading was added to the language itself, to the standard in C++11. Something else happened about this same time. All of this is about what happened about 2010, 2011. What happened then? Well, what I'm telling you now is about LLVM and Clang. Now, this didn't start in 2011. It had actually been going on for about 10 years. However, it got interesting for C++ in about 2011, 2012, because that's when Clang was complete enough to support C++. Clang had for a number of years been able to support C, but C is a much easier compiler to write. And then it wasn't useful really for C++ until about 2011, 2012, something like that. The two most important things about Clang, and the reason we want to talk about them is, one is competition. It set a whole new standard for build performance. Now, we're not talking about the performance of code that's generated. We're talking about how quickly it could generate that code. And the other thing was the quality of error messages. And the impact that both of those things have had on other compilers is remarkable. The performance of other compilers in these two areas has dramatically increased because Clang simply set a standard that other compilers had to match. But the real impact, I think the long-term impact for LLVM is that it's actually a toolkit, and it's great for building sanitizers and for being able to test features, new features in the library. And I think the long-term impact we're going to see for Clang is on these areas. The other thing that came important in this time frame is that more and more software becomes open source. And it turns out that C++, because of templates, really, really loves to actually see the compiled, see actual source rather than just trying to compile link together object files. So it's really open source friendly. The other thing I want to talk to you about is the Standards Committee. Now, what happened in 1998? Well, we said membership in the Standards Committee fell off. People were not interested in the standard after the release. That's not what happened after the 2011 release. After the 2011 release, it was the opposite. People started to get interested in C++ because they recognized, hey, new features can happen here. Let's start working on it. And part of the reason is that tool vendors were following the release very, very closely. As I said, it was 4 or 5 years after the 1998 release before we had versions of compilers and libraries that actually supported the standard. That was cut to a year. In 2012, we had 2 different versions of compilers that more or less supported the standard, and that caused a lot of interest. And the response was so many new people were joining the committee that a whole bunch of new groups were created, study groups were created. SG14 was created in 2014, but this is actually what it looks like today. We have even more groups created, and there's a lot of interest in the committee. a lot of activity in the committee, and the committee has stuck to its practice since 2011 of releasing a new version of the standard every 3 years. So we have a version in 2014, 2017, 2020, and we are on track for a new release in 2023. So something else was started in 2010, and that was an organization devoted to promoting C++. And I told you before that Bell Labs, where C++ was created, had used C++ and they saw it as an internal thing. So they never really marketed it. But the C++ Standards Foundation was created with the idea of actually marketing standard C++. And they created a website to promote it. And this is a great, the URL for this is isocpp.org. And it has lots of posts about all sorts of activity in the C++ world. One of the things that it also hosts is something called the SuperFAQ. Bjarne Strustrup, who's going to be on the program later with Ask Me Anything, he said he used to have a FAQ that he maintained for all the questions he got answered. There was also a C++ FAQ that came out of Usenet, and Bjarne and the Usenet FAQ merged their FAQs together and are now hosted on isocpp.org, which is why we call it the SuperFAQ. About 2015, a little bit later, a new product was released, a new IDE to support C, but most importantly, C++. Now, I'm not mentioning this because I'm not going to mention every C++ product, but I wanted to share some information that JetBrains' marketing team had come up with. And when I asked Anastasia for permission to share this, she said, be sure you tell people what our sources were, because she said, it's really hard to get this information. So we don't know really how good it is. We think it's the best, but that doesn't mean it's actually good. So what I'm going to share with you is from 2015 or actually before the 2015 release. So at that time, we believe there were about 4.5 million C++ devs. People now believe it's closer to 5.5 or even 6 million devs. As many C++ devs as Python devs, just from a total raw count, it's in the top 5 languages for number of developers. This is how it looks spread out. So I'm in North America. Most of the C++ programmers I know are in North America, so I have a very warped view when you understand that South America has almost half as many programmers, and Europe and Asia Pacific both have dramatically more programmers than we have in North America. So C++ is really a worldwide event. This is just kind of a distribution of the different industries that use C++. We have a dedicated podcast. This is the first podcast for C++ developers by C++ developers, and it's over 5 years old now. This is my podcast. Phil Nash and I do CPP Chat, and you can kind of guess what the URL for CPP Chat is. There are a couple of new podcasts. These are within the last year. One is called No Diagnostics Required. It's actually a JetBrains podcast talking about what's going on in the C++ world. The other one, Algorithms, Data Structures Equals Programs. You also have someone on the program, Bryce and Connor Hockster, do this podcast. And so you'll be hearing more for Bryce on the program today. There's other places on the net where you can get lots and lots of information about C++. The Reddit CPP has about almost 20,000 users on Reddit C++. And there's about 700,000 questions on Stack Overflow that have been tagged as C++. There is a very, very valuable reference from CPP Reference that is kept up to date. It already has things from C++ 23. They're not standard yet, but as they put things in standard, they get added to the reference. So this is an incredibly valuable reference for C++ programmers. There's also a community called cprogramming.com to support C and C++. And then there's also a Slack, a C++ Slack called CPP Lang. It has 177 channels, 20,000 members, and it is available for anyone if you go to this URL, you can get an invite and participate in this. This is what it looks like. This is just a particular user group with its Slack channel. There's also on the C++, the ISO cpp.org, there is a wiki there. And on the wiki, you can see a list of all user groups worldwide. It also tracks conferences. So this is kind of what C++ conferences looked like before, say, 2014. The two oldest conferences are, the oldest is ACCU, which is held every year in England. And then BoostCon, which changed its name in 2012 to C++ Now. Also in 2012, Meeting C++ was created. In 2012 and 2013, no longer, we had Going Native. And then in 2014, we had CppIndiaCon. And then after that, we've had a number of different conferences added, from regional, national conferences, or conferences focusing on a specific technology like audio development or embedded programming. And so there's been a number of different conferences all over the world, including, of course, CPP India. And we already have an announcement of a conference next year, a new conference in Canada, C++ North. And you can track all of these things on the ISO CPP website. So what I've tried to do is give you a little bit of background about why people are using C++ and why it was that after a disastrous decade starting in 2000, why C++ seems to have come back, why the beast is back. And so if we have any questions, Anchor, I'd be happy to take questions at this point.
Yes, John, but why did you stop? Please continue. Okay, yes. So thank you very much for sparing the time to go through the questions. I'll read out the top voted one as of now.
Okay.
What was the original implementation of C++? I guess C front. How was it used, and how could you please talk about it? Was that the case?
Yes. So so Bjarne worked on C front. So did Steve Dewhurst worked also on C front. C front, I think, is not often given a lot of credit, because the output from C front was not machine language, but was actually C. And so some people think, well, it wasn't really a compiler. It was just kind of a translator, which translated from C++ into C. And they're completely missing the point. The idea was just that why would Bjarne want to spend a lot of time writing a compiler to generate machine code when that already existed? C compiler does that. And he would have to write a compiler version for PDP and all the different families of computing. There's no point to do that. So what he did was he wrote a compiler where the output was C, and that was C front. This is actually kind of similar to what LLVM does, right? LLVM has a whole bunch of front-end compilers. They don't generate machine code. What they do is they generate this LLVM language, and then the LLVM is translated into different machine languages. So I did use C front. I didn't even want to think about what year that was. 95, maybe, something like that.
Wow. Superb. That's a long time ago. Okay, we go to the next one. C++ is good to write libraries, but can you enlighten us about ABI and why they break? There was another question about on the same lines. I've seen people like Herb Sutter talking about breaking ABI for C++. Could you please explain this from a beginner's perspective? Why would this be needed in C++ in future?
Okay, so let's think about this for just a moment. When we are writing in C++, I can make a library, and maybe I have a function, and it takes a couple of parameters. And as people use my library and there's suggestions for enhancements and new ideas, one of the things I could do is I could say, oh, yeah, this function would actually be better if I took a third parameter. But of course, if I do that, then I'm going to break all the existing code, right? So what I could do is I could give it a default value so that it behaves the same way if you call it with 2 parameters that the old function did. But if you have a 3rd parameter, we do something new. And that won't break any source code because the compiler will do the right thing. If you don't pass a 3rd parameter, it uses the default and then gets appropriate behavior. And if you do pass a 3rd parameter, the function takes that and uses it. The problem is that that function is going to look different from what the linker has created. And so it makes it impossible if you're writing new code and you want to link the new code to a library written with the old code. In other words, we've changed not the source API. The source API is fine. The way my library worked, it still continues to work from a user perspective. But once it's been compiled, now I have broken the ABI. This can happen in a whole bunch of different ways. You can break the ABI. If you have a class that is being passed around and you add a new data member to it, you change the size of it, and that also would break the ABI. So it wouldn't break the source. You can recompile if you have all the source. But the problem is there's an awful lot of companies that have one way or another invested in libraries that they may not have source to, or the library may be so old that they can't recompile it. They would have to do a lot of work in order to be able to recompile it. And so that's what the ABI issue is. The problem is that really holds us back because one of the complaints about the standard library is that there are certain things in it that aren't very because of the way they're specified, they can't be implemented as efficiently as we'd like. Maybe a hash table could be done more efficiently. But if we change the hash table, we break ABI. And so people are frustrated because the restriction to say, no, you can't make that change because it breaks ABI means the language is not improving in the way it should. And so we have this real tension because there are companies, one famous example is Google. Google has tons and tons and tons of C++ software, but they recompile from scratch regularly. They do not care about breaking ABI. If we could improve the language or the library by making a change, they would love that. But as I said, there are other companies, they may be, for example, shipping an operating system. And so they have a C++ runtime as actually part of their shipped system. And if they do an operating system update and we have a new C++ runtime, they could break existing applications. And then people are going to push back and say, we don't want to take your new OS because you would break our applications. So you see the tension. It is not an easy problem to solve. Some people are proposing, and I'm somewhat sympathetic to say, well, how about if we say every 3rd release? That's every 9 years. We break ABI on the 3rd release, and then we, plan for that. But that is contentious. And as I say, there's people on one side saying the standard doesn't say anything about ABI. And then there's other people on the other side saying, well, but you're going to break a lot of valuable software if you change the ABI. So that's the challenge.
Thank you for the answer. There was just one mention. So again, not spending much more time on this. Name mangling would be a solution to ABI breakage, was the question in quick.
I don't see how that would be a solution. So name mangling is one of the things, name mangling is essentially in C, because we don't have we don't have function overloading. Every function just has a name. That's the name of the function. But in C++, because we have a number of different functions that can be named foo, the way the compiler actually does it is they don't call foo, they call foo, and then they mangle the types of the, mangling just means incorporating the name, the types of the parameters. So you might have foo I is a foo that takes an integer, or it might be foo D takes a double. And so we name mangle in order to allow the linker to know the difference between the foo that takes a double and the foo that takes an I, right? So that's what name mangling is. Now, what the problem is if you make a change to a function by getting a new parameter, that's going to change the name mangling. And so maybe what you could do is, what you could do is you could introduce an overload that takes the additional parameter rather than using a default. So there's some tricks you can use, but there's some things you just can't do. And so, yeah.
Thank you. Swaminathan asks, at least two of the open pain points for C++ is a build system and packaging system. Do you think CMake and Conan is the answer?
Well, CMake is certainly the most popular system out there for builds. I completely agree that this is a huge pain point. In fact, I think it is the biggest technical problem in C++, and it's not. There is no easy, obvious solution. It's not necessarily something that the standards committee can do because it's not really entirely in their purview. We need tools. The standards committee can mandate libraries and compilers have to behave in a certain way, but the standards committee can't really say this is how build tools have to work. So it's a huge problem for us. And but there's a lot of really smart people who are devoting a lot of effort into it. And so I'm optimistic about it, but I recognize that it is not a solved problem and it is a big problem.
Okay, good. An interesting question for you specifically, John, because it asks, can C++ be the first language for someone who's starting learning programming? And you're a trainer?
I am a trainer. I will say that I don't train beginners. Not that I wouldn't love to do that. I would love to develop a class for beginners, but I mostly work for corporations, and usually they want me to, I think of it as they want me to take an intermediate programmer to be the expert programmer. And that's kind of what we try to do. But I do think that C++ can be a language for someone who starts to learn programming. What I do say about C++ is that, you know, it is for the reasons that I talked about in this talk. I mean, it's complicated. It has a lot of baggage from C. It's complicated. And what I mean by that is it's a professional's language. It is not a hobbyist language. So if somebody came to me and said, hey, I've made my fortune as an investor and I want to do programming because I think it'd be fun. I want this to be my hobby. And I'd say, you're going to love Python. But I probably wouldn't say, you know, unless they say, well, I really want to do games. Okay, maybe you are going to learn C++ after all. But for casual programming, for hobbyists, C++ is not necessarily the best language, but that doesn't mean it can't be a good one to start. In fact, because C++ requires you to understand the machine at a really fundamental level, in some ways, it's a great language to start with because you will learn programming techniques based on high-level abstractions. You'll learn about functional programming, you learn about object-oriented programming, but you'll also learn the difference between heap and stack. And I think many programmers today don't really understand the difference between heap and stack because they only use a programming language where objects always go on the heap and they don't really understand what that's about. And so I think that in some ways, starting with C++, although it's a challenging way to start, but it can be a really good way, particularly if you have good learning materials and you're not just, you know, thrown into deep water.
Good. I guess that the next one should be our last one. It's already 11:33. Can you share your views on Intel's One API and recent adoption of LLVM by Intel?
Yes, very easily and quickly, because I haven't been following this, and so I have no opinion on this at all. I wish I had something intelligent to say about this, but I don't know anything about this. And I think that I believe that Intel used to use the EDG front end and then wrote their own back end. And one of the amazing things about Intel is they write a pretty good back end, as you might expect. They understand that the instruction set pretty well. And so again, this isn't something I've been following, but having the Intel team work on LLVM, that's got to be great for everybody, right? That's going to improve LLVM, and yeah, so that's going to be a great situation there.
Okay, I see there are more questions in the Q&A, and I request everybody to go to the Discord channels. There is a channel called as General Discussion, and we perhaps already have a thread where it's a sub channel of the General Discussion channel. for John's talks. So all the questions which did not get answered, John, you would be around to take them?
I absolutely will. I'm in there now. I'm typing.
Thank you. Thank you very much. Oh, so it's already there. So please, I'll request, I'm sorry, there wasn't enough time to take all the questions, but you can always ask these questions to John directly on that channel. And at this point, I say a very,
thank you very much for having me. I'm delighted to be involved. C++ India. I'm just so excited about what you guys are doing,
and what a way to
really
start.
pulling for you guys.
What a way to start our first ever CppIndiaCon. So thank you very much from the bottom of all our hearts. We all thank you very much for all the talk and the knowledge and walking us through the history of C++. See you around.
Thank you very much.